The direct comparison test, when you take two infinite series, A sub n and B sub n, be very careful to note that A sub n is going to be less than or equal to B sub n, and both are positive for all values of n. First case scenario is if the infinite series of the larger of the two, B sub n, converges, then the infinite series of the smaller term will converge as well. The other way to look at that is if you have an infinite series and you have a smaller term that diverges, then the infinite series of the larger term will also diverge. We're going to look at examples of each case. For example, the infinite series from 1 to infinity, 1 over 2 plus 3 to the n. What you want to do is you want to find a very comparable term. 1 over 2 plus 3 to the n is very comparable to just 1 over 3 to the n. Get it very close to the original, and be very careful to do this. Remember that a fraction with a larger denominator will actually have a smaller value overall. So there's two reasons that I picked 1 over 3n. One is they're both positive, but also I knew that this one would be a geometric series with a ratio of 1/3. That makes it a larger term that also converges. If I can get a larger term to converge, then the smaller term in a series will also converge. So we know that 1 over 3 to the n can be written as 1/3 to the n. That r value from a geometric series would be 1/3. Since that's less than 1, we have a convergent geometric series. Therefore, by direct comparison test, the original infinite series is convergent too. Let's look at in the other case, case number 2. If we have an infinite series, 1 to infinity, of 1 over 2 plus square root of n, I know that I can make a smaller fraction by taking a fraction that's very comparable, but that I know is going to be smaller or larger. So let's look at this. Here's the original A sub n, and that comes from the series given. This is comparable to 1 over n. Now, if I'd have made that square root of n, I couldn't claim this, but I'm leaving it 1 over n. You pick any value of n that's 4 or larger, then the original term A sub n is larger than this one. I picked this one because I knew it was smaller, but I also knew it was divergent. And remember up here in this theorem, A sub n needs to be less than or equal to B sub n for all n. I know that the one that I have will diverge because it's a harmonic series. Also, you could look at it through the eyes of a p series where p is equal to 1. But anyway, long story short, this series is smaller than the one given, and if I can get a smaller one to diverge, then the larger one will diverge as well. Here's how you look at it overall. If you can build a larger one that converges, the smaller will converge also. If you can build a larger one, if you can build a smaller one that diverges, the larger one will diverge also. So you get a large one to converge, the one smaller will converge. Get one to diverge, the larger one will diverge as well. It takes some practice. There's also a limit comparison test that you might find a little bit easier to use than direct comparison. A limit comparison test, you have both A sub n and B sub n are both positive. Then you can take the limit as n goes to infinity over the one given. So you take the term given in your problem, create one that's similar, and if that ratio when n goes to infinity comes out with a finite positive value, then both the one given, the infinite series given, and the infinite series you choose will either both converge or both diverge. Let's look at an example, the sum from 1 to infinity of 1 over 3n squared minus 4n plus 5. I'm going to pick a sub n to be the original term from the series. I'm going to pick one using dominant terms. N squared is the dominant term, so the one I'm going to compare is 1 over n squared. Using limit comparison test, the original over the one I build, that's 1 over 3n squared minus 4n plus 5, divided by 1 over n squared is the same as multiplying by n squared over 1. As n gets really large, you're only going to have to worry about the dominant terms, the n squared on top, the 3n squared on bottom. In this fraction, there's an unwritten 1, and because n squared is the same, when n gets infinitely large, 1/3 will be your limit value. That's your L. Since 1/3 is positive and finite, we're in business. We can apply. 1 over n squared is a convergent p-series because p equals 2, and as long as that power is larger than 1, the p-series converges. Since our ratio had a finite positive limit, if I know one of the pieces, namely the one I chose up here is b sub n, if it converges, then the one given in the original problem must also converge. And again, that's by limit comparison test. An example of one that does not converge, let's look at a limit comparison where we have divergence. We have the sum from 1 to infinity of 1 over square root of 3n minus 2. The original problem, I'm calling that a sub n. The one that uses dominant terms and is very comparable, I can pick 1 over square root of n. They're very similar. Limit as n goes to infinity of the original a sub n over the one I've created, b sub n, is the same as the limit as n goes to infinity of 1 over square root of 3n minus 2 times the denominator flipped. That's going to give us square root of n over square root of 3n minus 2. In the denominator, I'm going to factor out an n. If I factor out an n, I've still got 3n minus 2 times 2 over n. Now the reason I did that is because I knew this fraction will go to 0. That leaves us square root of n over square root of 3n. By property of radicals, that's square root of n over 3n. And as n gets infinitely large, I'm going to get square root of 1/3. Those n's cancel, and that unwritten 1 coefficient, square root of 1/3. That's our capital L. It's positive and finite, so this is what I can claim. I know that the b sub n that I created won't add up to a particular sum because it's a divergent p-series. That's n to the half. P is equal to half, which is less than 1. That means it's divergent. So if the one I create is divergent, then the one from the original problem will also be divergent. You have to make sure that that limit is positive and finite, and then you should know something about the one you create, and that'll tell you what you need to know about the one from the original problem. I hope this video helps you out. If you have any questions, reach out by phone or email. come by the office or ask in class, and I'll do my best to help you out.